Thank you very much for attending this session. Today, I'm going to talk about process flow analysis. And the backbone of the process flow analysis is the Liddell's law. Our whole session today will be around the Liddell's law. Professor Liddell is a retired professor at UC Berkeley, but in the past 50 years, the name of the waiting line analysis and process flow analysis is tied with the name of Professor Liddell. He is retired, but he is still very active. And that is what we should also do. Work and appreciate life. Let me start with a simple problem. The problem is so simple that I'm sure all of you will get it. But the difficulty is this. As soon as we go to another example, not you, but many students have difficulties. Let's look at this situation. Suppose we have a container. That container has capacity of 100 gallons of liquid. And suppose a dense liquid comes into this container at the rate of 10 gallons per hour and goes out at the rate of 10 gallons per hour. That is the basic concept in all stable systems. Inflow is equal to outflow. Let's suppose each molecule of this dense liquid which comes into the system cannot go out until all the molecules that before it were there have gone out. So how long does it take for this molecule which just came in to go out? How long does it take? 100 gallons are there. We are emptying at rate of 10. So it takes 10 hours for the other molecules to go out, and then this one goes out. So that is simply 100 divided by 10, which is equal to 10. Flow time is 10 hours. Let's go through another similar example. Suppose here we have a container with capacity of 9, and suppose 9 gallons of that liquid, of that dense liquid, are already there, and liquid at rate of 9 gallons per hour come in, and at rate of 9 gallons per hour goes out. How long does it take for this molecule, which is in a fraction of a second to come into the system, to go through the system and go out? How long does it take from this point to this point? For this molecule to arrive at this point, everything else before it should have already gone out. So we need to empty this 9 gallons. And we are emptying them at rate of 9 per hour. So it takes 1 hour. for this molecule to go out. That is the flow time. What about this one? 20 gallons are there. Flow at rate of 1 gallon per hour comes in, and at rate of 1 gallon per hour goes out. How long does it take to empty this? Indeed, we empty this, but other flow come and fill it out. So this container always has 20 gallons. This one always has 9 gallons. And this one always has 100 gallons on average. So it takes 10 hours for a flow unit to pass through this process, 1 hour to pass through this process, and 20 hours to pass that process. Now let me make the problem a little bit complicated. Not complicated, but a little bit not very easy. Suppose out of this 10, 9 goes here, and out of this 10, 1 goes over there. And here, this is 1, and this is 9, so 10 goes out. Now we have a system. System is a set of components and a set of interrelationship between them. We have a system. 10 gallons per hour comes in, 10 gallons per hour goes out. All flow units pass this one, but some flow units go this way and some flow units go this way. So a mixed blue and green comes in, a mixed blue and green goes out. Blue and green both go through the first process, green goes through the bottom process, blue goes through the top process, and then they go out. How long does it take for a molecule of this liquid from the time that it comes in until the time that it goes out? Let me answer this question by going through another problem. So we have a coffee shop here close to the intersection of Plummer and Reseda. The door of this coffee shop opens once every 1 minute on average. And one customer comes in. In a stable system, if one customer comes in per minute, on average, one customer should go out per minute. Input should be equal to output in long run. For 1 hour, for half an hour, it is possible that input is greater than output or output is greater than input. But in long term, input is equal to output in all stable systems. If input is greater than output, people will be there, and what will happen after 1 hour, 2 hours, 3 hours, 4 hours, 5 hours? There will be no room for anyone to enter that system, and system collapses. What will happen if what goes out is greater than what comes in? It is impossible. For 1 minute it is possible, for half an hour it is possible, for 1 hour it is possible, but in long term it is not possible. How could number of people who go out be more than number of people who? In long term it is not possible. Therefore, for example, every 5 minutes, 5 customers come in and 5 customers go out. Or at least the total number of people who come in per day is equal to the total number of people who go out. And therefore, when we divide it by the number of hours and the number of minutes, on average, What comes in per minute is equal to what goes out per minute. What comes in per hour is equal to what goes out per hour. What is the throughput of the coffee shop? Throughput of this coffee shop is one customer per minute. One customer per minute comes in, one customer per minute goes out. We show it by R in the Little's law. R in this problem is equal to 1 per minute. Throughput is the flow rate in a stable system. Stable system input is equal to output, and throughput is average of this flow rate. Flow rate goes up and down, but throughput is the average of it. Throughput is 1 per minute or 60 per hour. And if the system works for 10 hours, then it is 600 per day. Throughput always carries a time component with it. How, at what rate people or products come in and go out. So if you go back to the original problem, the containers that I explained, over there, throughput of the first container was 10, throughput of the container in bottom was 9, and throughput of the container on top was 1 per hour. Throughput of the system was 10 per hour. And if a day is 24 hours, then throughput over there is 240 gallons per day. Inventory is what is inside each gallon or what is inside all those gallons. Inventory of the first gallon was 100. Inventory of the gallon in the bottom was 9 gallons. Throughput, 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 throughput has a time unit associated with it. 10 per hour, 1 per hour, 9 per hour, 1 per hour, 9 per hour, 10 per hour. Throughput has a time unit associated. Inventory is a number. 100 gallons, 20 gallons, 9 gallons. There is no time associated. Inventory is in numbers. Indeed, throughput translates inventory from numbers to time. That is what the Little's law does, to change the dimension of inventory from unit to time, and we will see. So inventory in the coffee shop is the average number of people who are in waiting line. And the data of the problem tells us there are always 4 people waiting and 1 person is at service. So 5 people on average are always inside the system. In real life, these 5 people sometimes is nothing, sometimes is 10. On average, they are 5. You may imagine that we think we are in an airplane far above, and then we look at the general patterns in a stable system. So throughput is 1 per minute, and 5 people on average are there. As soon as 1 person leaves, these people come forward and another person will come in, and on average, always 5 people are there. What is inventory? Inventory is 5. On average, 5 customers are in the coffee shop. Inventory, we show it by I. R is equal to 1 flow unit. Flow unit is the general term that we use it a lot. In this coffee shop, a flow unit is a customer. In that example which we were discussing before, a flow unit is a molecule of that dense liquid. How long does it take on average for a customer to go out? Very simple, the same as what we discussed before. It's a container with 5 molecules, empty it at rate of 1 molecule per minute. Therefore, flow time is equal to inventory divided by throughput, and that is 5 divided by 1, which is equal to 5. 5 what? 5 minutes. Why? Because this throughput is in terms of units per minute. Let me provide you with another explanation of the Lidl's law. We have 1, 2, 3, 4 customers waiting here, and 1 customer is with the server. This is the server, the processor, okay? And another customer is about to arrive. This customer is about to arrive. And this customer is with the server. Exactly in the fraction of the second that this customer wants to come in, this customer is in the last fraction of second to leave. This customer is almost here. It has a fraction of second to go out. This red goes over there, this red goes over there, this red goes over there. Therefore, this is red, this is red, this is red, and this green comes in here. So in the fraction of second that this customer is going to leave the system, looks back over its shoulder. How many people he will see or she will see here? 5. 5 people are there. That is inventory when this customer is leaving the system. These people came in at what rate? At rate of 1 per minute. When this customer came in, when he was in this situation, when he looked over his shoulder, he saw nothing. Now when he looks over his shoulder, he sees 5 customers. 5 people are there. They came in what rate? 1 per minute. How long does it take for 5 customers to go behind him? Because at the first time when he was going to come into the system, he looked over his shoulder and he saw nothing. Now when he is leaving the system, he looks over his shoulder and he sees 5 people. Those people came in at rate of 1 per minute. It takes 5 minutes for 5 people to come in at rate of 1 per minute. Therefore, from the time that he had no one behind him up to the time that he sees 5 people behind him, it took him 5 minutes. to go from this point to this point, and that is what we call it the flow time. Flow time is equal to inventory divided by throughput. Flow time was equal to inventory divided by throughput, and therefore throughput times flow time is equal to inventory, and that is the Liddell's law. So again, throughput here was 1 per minute, or we can say 60 per hour, or if the shop works for 8 hours, you may say 480 per day. In all these cases, we will get the same results. For example, suppose R, instead of 1 per minute, R is equal to 60 per hour. Throughput times flow time is equal to inventory. Throughput is 60. Flow time, we don't know. Inventory is 5. Therefore, flow time is equal to 5 divided by 60, or 1/12. Here we got 1/12. Before we had 5. Are they the same thing? Yes, because 5 is 5 minutes and 1/12 is 1/12 hours, and 1/12 hours is 5 minutes. So here we have shown that if I have 100 of item A and 1,000 of item B, but if throughput of A is 4 per day and throughput of B is 200 per day, here 100 divided by 4, that is 25 days of inventory. But 1,000 divided by 200, that is 5 days of inventory. So this 100 is more than these 1,000. I encourage you to read these slides, slide 10 and slide 11. Inventory is measured in several dimensions: space, units, time, and value. Now let's make the problem a little complicated. Suppose 40% of customers who come into this coffee shop at Plumbers and Reseda, 40% of them go into the second line when they get exotic coffee or whatever. And 40% of them, as soon as they are done here, they leave the coffee shop. 40% go there, and on average, 4 people are in the second line. How long does it take a person who gets a black coffee and leave? How long does it take a person who get an exotic coffee and leave? And how long does it take a person who comes into this coffee shop? He is a prototype customer, is a mixture of these two. How long does it take him or her to come into this coffee shop and go out? What is the average flow time? Don't tell me that 4 is too much, because we don't have any control on that customers in the second line. It depends on how fast the person who is in charge of exotic coffee is doing his job. So it is possible that we have 4 over there, or 10 over there, or 2 over there, or 20 over there. It depends on the speed of the person who served that part of the system. Again, 1 person per minute comes in, 60% get black coffee and leave, 40% exotic coffee. In the first line, 5 people. In the second line, 4 people on average. What is the flow time of a person who get a black coffee, exotic coffee, or in general, what is the flow time of a customer? So here is the line for everyone. Throughput is equal to 1 per minute. Inventory is equal to 5. Flow time is equal to inventory divided by throughput, and that is 5 divided by 1, which is equal to 5. 5 what? 5 minutes, because throughput was in terms of minutes. T1 is equal to 5. Throughput is equal to 1 per minute. But 40% of it goes this way. Therefore, 40% of 1 is 0.4. 0.4 per minute goes through this line. 0.6 per minute goes out. 0.4. 1 per minute will leave. Therefore, if we look at this system, throughput is 0.4 per minute, and inventory is 1, 2, 3, 4. Throughput 0.4 per minute, inventory is equal to 4. Therefore, flow time is equal to 4 divided by 0.4, and that is equal to 10. Therefore, it takes us 10 minutes to pass this line, and 5 minutes to pass this line. People who get black coffee, they will be there for 5 minutes. People who get exotic coffee, 5 minutes, and they will be over there for 10 minutes. That would be 15 minutes. Therefore, we do have two classes of people. One group get black coffee or something close to that and leave in 5 minutes. The other after staying 5 minutes in the first line, they go to the second line, and they will also be there for 10 minutes, and therefore it takes them 5 plus 10, 15 minutes to leave. How long does it take a customer to come into this system, get what he or she wants, and leave? There are 3 ways to answer this question. The first 40% are there for 15 minutes, and 60% are there for 5 minutes. That is equal to 6 plus 3 equal to 9. Therefore, an average customer will be in this store, in this coffee shop, for 9 minutes. It is a mixture of those people who get black coffee and those who get exotic coffee. The second procedure can claim everyone will be there for 5 minutes. Everyone, no matter he or she gets black coffee or exotic coffee, that person will be there for 5 minutes. So 5 is there for everyone. Only 40% of people will be there for 10 more minutes. So that is 5 plus 0.4 times 10, which is equal to 5 plus 4, and that is 9. There is a third procedure. which does not need to go through who gets black coffee, who gets exotic coffee, or so on and so forth. Therefore, if the system is really complicated, we really do not need to go through details. We draw a line around the total system. Throughput is equal to 1 per minute. 1 per minute. Any objection? No. Inventory is equal to 5 plus 4, which is 9. Throughput times flow time is equal to inventory. That means 1 times flow time is equal to 9, and therefore flow time is equal to 9. 3 different ways to compute the flow time of a flow unit, a prototype flow unit inside this system. Now let's go back and look at the 3 containers that we have at the beginning of this discussion. 10 comes in and 10 goes out. If I ask you what is the flow time in this system, how long does it take a molecule from this point to this point? Your answer is quite simple. Throughput is equal to 10 per hour. Inventory is 100, 120, 129. Inventory is equal to 129. Therefore, flow time is equal to inventory divided by throughput, and that is 12.9 hours. You can go through detailed computations and find it out. How long does it take to go through this pass, and how long does it take to go to the other pass, and then compute the average. Weighted average, of course. I encourage you to go through all these slides and read them beside watching the lecture. Of course, if just by reading them you understand the material, then you really don't need to watch the lecture. But I have explained everything in detail in these slides. Now we have a different system. We have this system. Customers coming at the rate of 1.5 per minute. We have 6 people here, and we have 3 people here. This is the original line, this is the exotic line. 1/3 of customers go this way, 2/3 go this way. What is the flow time of the customers who get black coffee and leave? What is the flow time of customers who get exotic coffee and leave? And what is the flow time of a customer? Flow time here, T1, is equal to inventory, which is 6, divided by 1.5, and that is 4 minutes. So it takes 4 minutes to go from this point to this point. Those people who get only black coffee, they will be there for 4 minutes and leave. So 4 minutes is the flow time of the customers who go only through the first process. For the second process, 1/3 of 1.5 will go through there. 1/3 of 1.5 is 0.5 per minute. So flow comes in at rate of 1.5 per minute, then it goes through 2 branches. 1/3 of it, which is 0.5 per minute, goes through this branch. 2/3 of it, which is 1 per minute, goes through the other branch. So here throughput is 0.5 per minute and inventory is equal to 3. Flow time is equal to 3 divided by 0.5, and that is equal to 6. So it takes 6 minutes to go through this line. Now, how long does it take to pass through this system? 2/3 will be there for 4 minutes, and 1/3 will be there for 6 plus 4, which is 10. That is 8 over 3 plus 10 over 3, which is 6. So on average, a prototype customer will be there for 6 minutes. Those people who get black coffee and leave will be there for 4 minutes. Those who get exotic coffee will be there 6 plus 4 minutes, which is 10 minutes. A different way to get the same results. Everyone should go through the first line, so it takes 4 minutes. 1/3 of people go through the second line, so that is 1/3, and second line takes 6 minutes. The other 2/3 will go through this line, which takes 0 minutes. That is why we even don't need to write it. 6 times 1/3 is 2, plus 4 is 6. Finally, we may also say this is the total system. 9 people are there. That is inventory and throughput is equal to 1.5. Throughput times flow time is equal to inventory. Flow time is equal to 9 divided by 1.5, which is 6. I have put very detailed explanations of what I did on these pages. You may go through them. Thank you very much for paying attention to this talk. I will put a set of examples, a set of simple examples to help you to feel the nature of the Liddell's law. Please watch them too. And then I will go through a little bit other problems.